In this second video for section 9.5, still kind of talking about alternating series, but we add two new definitions to this, and it's absolute and conditional convergence. Okay, so I'll take a look at kind of what happens when we might have a series that converges absolutely versus conditionally, and I'll describe those, and I'll write out the definitions, and I'll show you some examples here. I want to start with an example of a series that we have, say, from 1 to infinity of sine of n over n squared. If I write out a couple of terms here, I see sine of 1 over 1 plus sine of 2 over 2 squared is 4, sine of 3 over 9 plus sine of 4 over 16, so on and so forth. And I'm going to do some decimal approximations for you here. Those are not nice values of sine that we know. The first three terms we get here are positive. First three terms we get are positive, and then all of a sudden sine of 4 is negative, sine of 5 is negative. You might think this is alternating because we know sine of n goes kind of between -1 and 1, right? I'm going to use that to my advantage. But this is not an alternating series, right? Remember, from one term to the next, we have to be switching signs, and that doesn't happen. This is not alternating, okay? But it's close, it's similar. It's not geometric, it's not p-series, it's not telescoping. But there's something else we might try to do here. There's another theorem that might work for us. You can think about it as another test, though I don't typically. It will show up in our definition for absolute and conditional convergence. But what we have here is what's called the absolute convergence theorem. Absolute convergence theorem. And what this theorem does is it says the following. Let me write it down. If the series absolute value of a sub n from 1 to infinity converges, then we can directly say that the series without the absolute values also converges. Okay? So I'll do this every once in a while. It can be a quick check to just kind of drop absolute values, check that series with the absolute values around the nth term to determine if the series without the absolute value converges. We can use this to our advantage. And I'm going to do that with this series here. Okay? I'm going to take absolute values and try to do something to determine convergence then. Now, I'm not going to be working with exactly the same series, right? Series with absolute value and the series without are two different series, right? But because of this theorem, I can use one to tell me information about the other, okay? This theorem does not work both ways, right? So I can't just say, oh, well, a sub n converges, that series, so the one with absolute values should also converge. In fact, that's what it means to be conditionally convergent. We'll get there. Let's look at this example here where I have sine of n over n squared. Let's check absolute value version. Okay, if that's a sub n, then what I want to do is check the series with absolute values there. So I'm going to put absolute value around the nth term. I get sine of n over n squared in there. And I can simplify that a little bit here. In the denominator, I'm just going to get n squared because n squared is already positive. In the numerator, I have absolute value of sine of n. Okay, this guy is what I'm going to want to try to replace or do something to it to help this look like another series. Okay, what do I know about sine of n? Like I said before, sine goes between -1 and 1. So sine of n also is going to go between -1 and 1. That's another way of saying that absolute value of sine of n is less than or equal to 1 in absolute value, right? So this sine is going between -1 and 1. That means the size of sine, the magnitude, the measure of sine, is always less than 1 in absolute value. And we can also say that it's positive, okay? So what we've got is then the following thing. What we can do is say, since sine of n over n squared, since sine of n in absolute value is less than 1, I can say that this fraction is less than 1 over n squared, which is of course a p-series. and it's a convergent p-series with p being 2. Okay, so I have taken absolute value of a sub n, right? I've looked at a different series. That series is smaller than a convergent p-series. So by direct comparison test, since 1 over n squared converges and it's larger than the series that I have, then I can say so does absolute value of sine of n over n squared from 1 to infinity. So the series with absolute value converges. Let me go to the next slide here. Since this guy converges, the one with absolute values, by the absolute convergence theorem, I have that the sum of sine of n over n squared from 1 to infinity also converges. Okay? So I'm using that theorem to my advantage there. I looked at the different series that absolute value of a sub n, that converged. So because the absolute convergence theorem, I can say that the series without the absolute value also converges. Okay? So in short, what we did, we can quickly check or quickly test the convergence of the sum of a sub n by checking the convergence of sum of absolute value of a sub n. But what if the sum of absolute value of a sub n diverges? All right, that's kind of the next follow-up question. What if we were to take the absolute value and we got a series that was divergent? And actually that quickly would happen if my series was a little bit different, say sum of sine of n over n. That would happen to be a divergent series if I were to take absolute value. All right, if I were to take absolute value, this would look like 1 over n, which is the harmonic series, and we know that that diverges. What happens in this case? This is going to lead us to our two definitions here, where we have absolute convergence and conditional convergence. First is that the series is absolutely convergent or converges absolutely when the sum of the absolute value converges. Right? That's really basically like our absolute convergence test. It's not much different, but we're just calling that now absolute convergence or absolutely convergent. The second is called conditional convergence. It goes like this. The definition, the series a sub n is conditionally convergent when we have the original series converging, but the absolute value series diverges. Okay? So that's kind of that what if situation I was just talking about on the previous slide. If we take absolute value, if we look at that series and it diverges, well, we keyword might, have a conditionally convergent series then. I'll show you what happens. So let's look at an example here. This guy is actually absolutely convergent because we take absolute value sine of n over n squared, we found that that converged. So since that series converged, we can say that the kind of, original series, this guy here, converges absolutely by definition. Okay? But as I was alluding to a little bit, slightly kind of a different maybe example, the sum of minus 1 to the n over n is called conditionally convergent. And I'm not going to go through everything here, but because this guy, when I take absolute values, I end up with the harmonic series. That guy diverges, but we're able to show that the original series there converges. We'd have to use the alternating series test. Okay, so there's just two kind of quick examples of a conditional convergent and an absolute convergent series. And I want to do an example here, just one, I think, of where I go through and show you how to determine if a series is absolutely convergent or conditionally convergent. So here's my series. minus 1 to the n plus 1 over n plus 2. Determine if the series converges conditionally, absolutely, or not at all. Conditionally, absolutely, or not at all. Okay? So there's a chance that this guy just doesn't converge at all. All right? So basically, what we want to do is to look at this series and also the series where I take absolute value. So I'm going to check convergence of the absolute value of that a sub n there. And if I do that and the series converges, if this other series converges here, then I'm done. Because my absolute convergence theorem applies, and that's it. I have an absolutely convergent series. However, if this series here, underlined there, diverges, well, then I have to check whether the original series converges just by itself or not, without the absolute value. When I take absolute value of that a sub n, that nth term, the negative 1 to the n plus 1, the alternating part goes away. Yeah, goes away. So what I have is the sum of 1 over n plus 2. This looks like a p-series. Looks like p-series. It looks like the harmonic series, right? When p is 1. So what we can do is try to compare, because it's not exactly that harmonic series. So I take 1 over n plus 2 and I try to compare it. But the inequality isn't really going the way I want it to, right? 1 over n is larger because 1 over n plus 2 has a larger denominator. Larger denominator means 1 over n plus 2 is smaller. So I have a larger divergent series, which doesn't really help. All right, that doesn't apply in my direct comparison test. So we're stuck with the limit comparison test. I'm comparing 1 over n, which I know diverges, to 1 over n plus 2. My limit here, I'm going to multiply by the reciprocal, n plus 2, then an n in the denominator. Splitting things up, since I have a single term in the denominator, limit of 1 plus 2 over n, which is, of course, 1 plus 0, or 1. Since this result, that limit, is positive and finite, I can say, since 1 over n diverges, by the limit comparison test, so does the sum of 1 over n plus 2. Okay? What's going on? I've taken absolute value of my original series, okay, to hopefully check if the different series with the absolute values converges. If it were to have converged, I would be done. But we have shown that the series with absolute value actually diverges. Okay? So we have kind of two potential outcomes now. Either this original series, minus 1 to the n plus 1 over n plus 2, either that series just completely diverges or it converges conditionally. Okay, and the only way we're able to determine if it converges conditionally is if the series itself converges. Now, why didn't we just check that to begin with? Well, what test would we use to determine if that original series converges? We would check the alternating series test. But the alternating series test doesn't tell me if a series converges conditionally, absolutely. Okay, so that's why we have to check this absolute value version in order to make any sort of assessment on absolute or conditional convergence. So, given this series here, just the a sub n one, the original series in the example, we determined that the sum of absolute value of a sub n, which is 1 over n plus 2, that guy diverged by the limit comparison test. Okay? So now what we have to check is check for conditional convergence. So we look at this sum of a sub n, the original series, to determine if it converges. Okay? Remember, conditional convergence is when the original series converges but the absolute value diverges. Okay? So I use alternating series test here because my original series is alternating. My C sub n is 1 over n plus 2. So I have to go through my two conditions. One, I have to take a limit of C sub n, a limit of 1 over n plus 2, and of course that's an easy one. That limit is of course 0. 2, I can take a quick derivative here of 1 over n plus 2, and I get minus 1 over n plus 2 squared. And that's, of course, less than 0. That's, of course, negative. That means that C sub n is decreasing, right? That means that C sub n is decreasing. So what I'm able to do then is say from the alternating series test, the sum of minus 1 to the n plus 1 over n plus 2 converges by the alternating series test, and therefore converges conditionally. Right? And it converges conditionally again because up top here we determined that the absolute value diverged and the original series then converged. Okay? So a lot of the tests that we know so far, integral, p-series, geometric, comparison, none of those tests will tell us if a series converges absolutely or conditionally. Okay? So far, the only thing that does that is if we use to our advantage this absolute convergence theorem. And we check those definitions. We check if the sum of absolute value of a sub n converges. If it does, we're done. If it doesn't, then we have to go back and check if the original series converges or not. Right? This is absolute and conditional convergence. Thanks for watching.